And like you said, I've got this set up to record.
Oh, okay.
Right.
Okay, now it's 5:42. So let's continue today's. Let's talk about today's SEM. So last week we reviewed some part of the math preparation and also some stats, but we didn't finish that part. So we're gonna finish the. Oh, I just turned it off. Is that better? Is that
No,
better?
it's better with it off.
Is this better?
Yes.
Sorry. But when I write something on the board, I will turn it on. Okay. So we're gonna finish that review first in the first session. And then in the second session, we will formally move forward to the SEM. Just a background introduction. Okay. The first SEM model, maybe in the history. And then we're gonna look at path diagrams. As I mentioned, the path diagram is another way to show our model. It's very popular. It's very useful. It's very, yeah. It's gonna give us some visualize the SEM version. Okay. And then we will look at the math equations, including Liesel model and the Bender-Weeks models. All of these are mathematical equations. I will do the explanation of each notations and the meaning of those equations. So that's the outline for today's talk. Yeah, so let's finish previous review. So let me open the review slides. So we finished the matrix part. We talk about the random variables, expectation, variance, covariance, correlation, and I think we stopped there. And then we're gonna finish all of the remaining parts. Yeah, so we talk about the population version of covariance and correlation, and also we have sample version of covariance and correlation. Okay, so that's a formula for sample version covariance, and we have a term called sum of cross products. That is the product of two deviation scores, one for X, one for Y, and the cross product and the sum of the product. Okay, so these are deviation scores, not the original raw scores of X or Y. And correlation is another version of covariance. We just use the standard deviation of X and the standard deviation of Y to standardize covariance or to normalize the covariance. This is the covariance. This is the covariance of between X and Y. And the bottom part, one component is standard deviation of X. The other component is standard deviation Y. Okay, divided by these two, we're trying to normalize or standardize the covariance between X and Y. So in this case, there's no unit for correlation because the unit for covariance has been canceled by the standard deviation of X and also the standard deviation of Y. So there's no unit. We only needed to do the comparison between these numbers. Okay, so which one is larger, which one is smaller, just look at the numbers. And because it has been standardized, the maximum value of correlation is 1. Okay, the absolute value of correlation, the maximum value of absolute value of a correlation is just 1. You cannot get a correlation which is larger than 1. So if you do your calculation and you got a number 3.5 or 50, that's obviously wrong. So you need to go back to check why there's the correlation which is larger than 1. Okay, and of course it could be -1, it could be +1, any number between these two numbers. Okay. And we have some properties for expectation and variance. So
So it doesn't have to be exactly 1, but it can be like a 0.5.
Sure,
As long as
definitely.
it's between the 2 bookends.
Sure. If the correlation is 1, what does that mean? First, it's positive. Positive, what does that mean? If X is large, Y is large, that means positive correlation. 1 means perfect prediction. If I know X value, I know the perfect, how can I say that? It's just a straight line. There's no random because of the correlation is 1. So
Sorry.
oh, that's okay. So where are those markers? It should be here. Where are those?
I have one more, if you have a hand sanitizer, you can wipe it out.
That's okay. I think I can find it somewhere. Maybe someone just took it.
If you would like to just ignore my question, that's fine. I'm sorry. I didn't mean
Okay.
to do a tangent.
Okay. So I don't have anything ready. So okay.
You want to use it?
Okay. Yeah. Thank you.
You're welcome.
Thank you.
You're welcome.
Wow,
That's a student
great.
prepared.
So I don't know how to use that.
I'll just take the top out, the book part out, the other part.
Oh, this part.
Yeah.
Okay, good. Thank you.
You're welcome.
Okay. So if we have positive correlation, that means, okay, so the direction is just like this way, okay? So if we have a larger, for example, this is X, this is 1. If we have a larger X value, then the Y value will be larger. But if it's negative direction, then if it's negative, the direction is just like this way.
As X
With
gets
a,
larger,
yeah,
Y
with
gets
a
smaller.
larger X value, the Y becomes smaller because it's negative correlated. Okay, so then becomes this way. So if the X is become larger, the Y becomes smaller. That's the direction, but the number, the magnitude, you may have some dots like this. Okay, you have some X here, you have some Y value here. So you can see that in this data plots, it's positive. But how strong? It's quite strong because you can see that with the value of X, you can actually look at the Y value is quite close to the expected value. Okay, but if it's 1, then it's perfectly correlated. But sometimes you may have a lot of like loose dots, something like that. Okay, then the correlation between X and Y are actually really small. It could be 0 because you cannot tell Y if you know of the value of X. Okay, so just association, the association between X and Y, we quantify that association by our real number between between -1 to +1.
Yes, ma'am. Thank you.
Okay. So let's look at the properties of X and this is the matrix card. Oh, I forgot. I'm sorry, I forgot the Zoom. So some student asked me to have the Zoom open.
I'm actually recording this in Zoom.
Oh, because she's taking right now. Yeah, she asked me to use a Zoom. Yeah, if you feel uncomfortable, if you have any COVID symptoms, you can just request me to use the room and I will open it for you. Yeah, this is the document in the ELC about expectation, properties of expectations and variances.
You're muted. She can't hear you. You're
Oh.
muted on Zoom. She
Oh,
can't
yeah,
hear
yeah,
you.
yeah, you're right. I needed to share this part. Yeah. I forgot, did we go through this part? Did we go through the properties last time? Or haven't? Let me see. Expectation. Did we talk about those properties? We talk about the definitions.
I believe we did.
Yes.
We have already gone through this part.
Yes.
Okay, so yeah, so the rules for expectations, the rules for variance. Okay, then that's good.
Man, you're
Yeah.
still muted on Zoom. She can't hear you.
Oh, I'm sorry. So yeah, okay.
Up top. Sorry, I didn't mean to keep interrupting.
I'm not familiar with the Zoom in this lab. The other slides. This one. This one. Yes. Okay. So we have already gone through the properties of expectation and variance. Let's look at the properties for covariance. And I believe these slides should be important. Again, in your homework, you will do the similar algebra calculation. So let's look at some examples. So suppose, okay, let's look at the covariance. Okay, suppose we have two variables, X and Y, two random variables. And if we know that the W is the linear combination of X and Y, so we can use different ways, A or B, to combine X and Y together to get the W. Z is another random variable, which is another linear combination of X and Y. So here we have C and D. So W and Z are linear combinations of X and Y. And the A, B, C, D here are all constant, okay, not variable. So if we want to calculate the covariance between the new variables W and Z, how? Okay, just use the rules of covariance and also rules of the basic algebra. So the W, look at this equation, is 8x plus by. So replace W by using this expression, okay? Z, again, by using this definition is cx plus dy. So just replace B by using this term. Next, you're gonna expand this part. So here we have sum of two terms. Here we have sum of two terms, and how to expand it by using the rules of covariance. You have these four terms, okay? Covariance between the first term of the first variable here and the first term of the second variable here, okay, ax and cx. So this is a covariance between these two components, variables. And then the first component for the first term and the second term, okay, dy of the second component and the covariance. And then covariance the second term here and the first term here. And then covariance the second term here, second term here. So finally, you expand the previous covariance into sum of four components. So now you have this sum, next part, just like the rules of covariance or the expectation, you're gonna take out the constant outside of this covariance calculation. So here we have constant A, we have constant C, take it out, take these two out and product. The remaining part is a covariance between X and X, because here we have X left, here we have X left. So after we take out those constants out of the outside of the covariance, we have this part, and we need to time A and C. Same thing, here we have A and D, both are constants. You take them out. Oh, actually, I have already combined some terms. Actually, you need to do this and take out this. And then you combine similar terms. So if we want to do the detailed calculation, okay, yes, thank you. So actually from here to here, I skipped one step. So this term becomes this term, okay? And this term becomes A times C and the covariance between X and Y. And this term becomes B times C times covariance between Y and X. Okay, Y and X. And this becomes this term, okay? B times C times covariance Y and Y. But here you have covariance between X and Y, covariance between Y and X. It's exactly the same because covariance is the association between two variables. If you change the order, it's the same. So these terms are exactly the same. Then you're gonna combine these two coefficients together. So here, you combine these two coefficients AD plus BC, and then times the covariance between X and Y. So finally, you have this term. And those terms are from the original X and Y. These, what is this? Covariance between X and X is the variance of X. Okay, this one is variance of X. Covariance between the variable and itself is just a variance. So this is a variance of X. And this is a variance of Y. Okay, covariance between Y and Y is variance of Y. And this is a covariance between X and Y. Okay, just copy this part, copy this part. So if you know the original variance of X, original variance of Y, original covariance between X and Y, any combination of these two variables here, okay, this is the combination of these X and Y. Any combinations of these two variables can be derived by using the following calculation. That's important. And again, in homework of SEM, we will have mediation model, moderation model. So we have some linear combination of known variables. And you are going to do the calculation to calculate the covariance between new variables, which those new variables are combination of the known variables. Okay, so that's an example. Okay, that's an example. If you are not familiar with these steps, you need to do the exercise after today's class. Okay, and if you don't know, just ask me or use my office hours. I will show you again. And a very special case of the calculation above. Okay, so variance between sum of two variables. Okay, so we have X plus Y, which is one variable. It's a sum of two variables. If we want to calculate the variance of the sum of two variables, again, you're gonna expand it. So variance of this one is covariance between of X1 and itself. Okay, X1 is here and itself. And you expand it like this way. So finally, you have variance of X, variance of Y, and 2 times covariance between X and Y. So this is a very special case. And also, this is also quite important. So I think everybody should really easy, yeah, to get this result, or you can just memorize this part. Okay, variance of a sum of two variables is the sum of two variances plus 2 times the covariance between these two variables. Okay, but again, let's look at another very special case. If these two variables are independent, X and Y, independent means, okay, the Y value does not depend on X value. So these are independent. In that case, the covariance is 0. So this term just disappeared. This term becomes 0. In that case, the variance of sum of two variables is a sum of two variances. Just variance of x plus variance of y. No covariance involved because the covariance here is 0. You don't need to worry about this part. So that's a very special case. You have to make sure these two variables are independent, and then you can use that formula. Otherwise, you have to consider the covariance between x and y. Okay, otherwise, you're going to miss an important component here. So that's a review for covariance. Okay, we reviewed the properties for variance. We reviewed the property for expectation. We reviewed the property for covariance for the calculation of combinations of variables. Okay, any question for this part? Any question for the review of expectation, variance, covariance, correlation, population version, sample version? Okay, so if we don't have any question, let's move forward to a very popular distribution called normal distribution. As I mentioned in the first review class, sometimes we only focus on one variable. Sometimes we focus on more than one, okay, 2 or 3, multiple variables. If we only have one variable and the variable have a normal distribution, we call it univariate normal distribution, univariate. So here, tilde, okay, why tilde? They should not be dot to dots, just tilde. Why tilde normal? For normal distribution, we have two parameters. Those two are called parameters. One is for the mean, central tendency, for the average. You can just think of the location, mean, average. The other one is for the measure of spread, which is sigma squared, okay, variance part. If you know these two parameters, a normal distribution will be fixed, totally fixed. So just like the plots here, okay, so these are all density function of normal. So these three, the golden one, the red one, and the blue one actually share the same mean, the same center. The center mu is 0 for these three. So the center point for these three curves are common, are the same, which is 0. They're located at 0 point. But if you look at the green one, actually the center has been shifted to the left side. The center shifted to -2 because the mu, the first parameter is -2. The center has been changed. Not only center, okay, let's look at spread, sigma squared. If you look at the golden one, the sigma squared is 5, which is large. Okay, so the golden one is widely spread. But if you look at the blue one, the sigma squared is 0.2, which is much smaller than 5. And then look at this curve, it's quite narrowly spread. So the sigma squared tells us the range, the spread. And the mu tell us where's your center, where's your location. You only need to decide these two values, and then the normal distribution will be finally fixed, okay? Of course, we have some other statistics, kurtosis, skewness, but for normal, you only need to know these, and the kurtosis and the skewness will be fixed. That's a visualized version of normal, but mathematically, how are we going to decide this curve? We have a math function. It's called a density function. Okay, again, density function we reviewed in the last week. Density function. This function tell us the probability, tell us the likelihood to obtain a special value. Okay, to get a value of y. So what's the probability to have this value? Because the outcome is actually uncertain. So you can have this value, you have another value. But I can decide your probability, although I don't know your actual outcome. So the probability is defined by this formula. So we have, okay, 2 pi square root, and under the square root sign, we also have sigma square. Sigma square is a variance of the normal distribution. And here, this is exponential. Exponential, the power term is y. This is observed y. And the mu is the center. Just like use this, you get the deviation score. Again, this is the distance of the observed y away from the center. The distance between the observed y and the center. And get the squared value. And then divide by 2 times the variance, sigma squared, the variance part. And forget to use the negative sign. So this is exponential value. So finally, you will have one number here. Also here, you have one number, one scalar times together. Finally, you have one number. That number is a probability. That number has to be between 0 and 1 because it's a probability. You cannot less than 0%. You cannot larger than 100%. So it has to be between 0 and 1. It's a probability. Again, if you do the calculation, if you got a probability which is less than, which is negative, then obviously it's wrong. Or you got number 1.7, which is opposite wrong because you cannot be larger than 1. It's a probability. And look at this, curve. Okay. So all the dots here, okay, all of these, the curve, the dots here shows the probability. Okay, the probability. Okay, that's our density function. We also have a good practice for mean and the covariance. Let's look at the sample mean and the sample variance. Again, suppose X is a random variable. It follows a normal distribution with mu and sigma squared. And because we're trying to look at the sample mean and the sample variance, suppose X bar is the sample mean. Sample mean, just use the previous definition, is sum of all of these observed variables divided by sample size n, which is the mean, average. And the sample covariance, again, follow the previous definition. Okay, got the deviation score squared. Okay, that gets the sum and divided by n minus 1. So that's a sample version of the variance. The magic thing is that these two statistics that are independent. Sample mean and the sample covariance are independent. Okay, so mean part and the spread part are independent. And also we have again, this should be tilde. I'm sorry, tilde. The distribution of this mean will be known if you know the original population of original definition of X. Remember, we have central limit theory. What is central limit theory? Okay, you know the X follow a normal distribution with mean of mu and the sigma square of variance, and then the mean of X, the average of X will follow, again, it's a normal distribution with the same mean, mu, with the same mu of the X. But the variance part, it's kind of like different. It's sigma squared divided by n. It's more narrow. It's narrower than the original distribution of X because it calculates the average. Average will shrink the spread. Think about a bunch of random variables. Okay, if you get this average, it's quite like towards to the center, towards to the mean. So it will much narrowly spread than the original X. So the sigma squared divided by n is the variance of the sample mean, X bar. Also, we have another good property. So this is the covariance. Okay, this is the sample covariance times n minus 1. It's kind of like the top part of the one. Divided the population version of the covariance. This is the sample version. This is the population version. Okay. So if you do the ratio, this ratio follows the chi-square distribution. Okay, chi-square distribution. We have a degrees freedom. Okay, this is the degrees freedom n minus 1. What is chi-square distribution? Actually, we have already shown the here. Those are chi-square distributions. Okay, so with different degrees freedom, we may have different shape. Okay, so for the red one, the degrees freedom is 1, then the chi-square just like a exponential way. Okay, if we have degrees freedom 2, then it becomes a green one. Okay, if we have degrees freedom 3, then it becomes a blue one. The degrees freedom is 3, then we have this the golden one. So with different degrees freedom, the shape, the distribution will be different. So the ratio of these two statistics follow the chi-square distribution with degrees freedom n minus 1. So all of these properties are really good, but that's only for normal distribution. Okay. Normal distribution is very powerful and also very popular. So very helpful for us. So that's for univariate normal. If we consider more than one variable, suppose we have x and y, or even we have z, okay, all of these together, then we can have an extension of univariate normal, which is called a multivariate normal. Multivariate, more than one, okay? Also, that distribution is the most popular assumption in our a lot of models. For example, SEM or HLM or multivariate, we use the multivariate normal distribution as our assumption. We assume the residuals have this kind of like a distribution. Multivariate normal also have a series of serious good properties. What are these? Okay, so let me show you some. Let me show you some good properties of multivariate normal distribution. Okay. Now we have more than one random variable. Suppose we have a lot. Suppose we have n random variables considered. So the y here is a vector, not a scalar anymore. So it's a. Can I use it? Thank you. Yeah. So let me connect on. Suppose we have a vector y, which consists of several random variables, y1, y2, y3, y4. So you can have a lot. Okay, because we have n. If you think about the GRE score, you can think about, okay, this y1 is GRE point, y2, for example, GRE verbal score, GRE writing score. You can also consider high school GPA or SATs, something like that. Okay, all of these are variables considered. I just include all of these as in Y. Y is a vector, a lot of variables. If Y follows multivariate normal distribution, what's the dimension here? So we have n here. Then we have, here we have n. Let's make it a k to distinguish the n normal and the subscript n. Suppose we have k, y here. Then the dimension here is k. We consider k variables together, which follow the normal distribution and the mean, center for the mean. The mean is also a vector. The dimension is k by 1, okay? K by 1. And we have a sigma. Sigma is the covariance matrix of all of these variables. So the dimension of sigma is k by k. Okay, is k by k. If k is 1, then the sigma, capital sigma square just becomes one scalar. It's just sigma. Okay. So if k is 1, sigma is 1 by 1. It's just sigma square. In our same as our univariate normal. If k is 2, the sigma becomes a matrix. What is the dimension of this matrix? If K is 2, what is the dimension of this sigma covariance matrix? It's 2 by 2. It's 2 by 2. That means we have 4 elements. We have 4 elements. What are these 4 elements? This one, okay, suppose K is 2, then we consider X and Y. Okay, we consider these 2 variables together. So this is a variance of X. This is a variance of Y. And we have a new element, the covariance between X and Y. And this is the symmetric matrix because it's a covariance matrix. So the element here is same as the element here. So it's sigma XY. So we have 4 elements in the case of K equals 2, 2 variables. If you only have 2 variables, then the sigma becomes this way. Of course, you can do it, you can continue this part. Suppose K equals 3. So you have X, Y, Z, 3 variables together. Okay, quant, GRE quant score, GRE verbal score, GRE writing score. So you have 3 variables together. Then in this case, the sigma here is 3 by 3. I have, in total, I have 9 elements, 3 by 3. Okay, now I have 3 by 3. So what are these elements? Suppose X, Y, Z. Then this is the variance of X. This is the variance of Y. This is the variance of Z. In addition to these 3 variants, we also need to consider the covariance because it's multivariate distributed. So all of these variables are correlated. We need to consider their association, covariance. Covariance between X and Y. Covariance between X and Z. Covariance between Y and Z. And again, it is a symmetric. So this element should be copied to this place. And this value should be copied to this place. And this value should be copied to this place. So there are 9 elements in total, but there are 6 different elements because 3 of them are the same, but they are different parts. So 3 variance parts, 3 covariance parts. So if we use the same example here, so what does that mean? If we want to decide the multivariate normal distribution of these 3 values, okay, on the verbal writing scores. So you needed to know the variance of verbal score. You needed to know the variance of the quant scores. You needed to know the variance of the writing scores. You also need to know the covariance between verbal and the quant. The covariance score between verbal and the writing, the covariance between the quant and the writing. And then you decide the whole distribution or multivariate normal distribution, okay? So, and you can tell, so when the K increases, it becomes more complex, okay? So that's the introduction of multivariate, but let's see why the multivariate is so important. Because we have a very good practice. For example, if Y as a multivariate normal distribution, then any subset of Y are multivariate normal distribution. So what does that mean? So suppose these K, okay, K variables together, it's multivariate normal. I can just take any subset. For example, quant and verbal, I just take these 2. These 2 follows a bivariate normal distribution because it's a subset of the whole section. I can take, for example, the writing score and the SAT score. These 2, or add high school GPA. These 3 can also, these 3 are also follow a multivariate normal distribution with dimension of 3. Any subset. Multivariate normal. Also, the marginal distributions are multi-normal, multivariate normal. So what does that mean? What is marginal distribution? So here we consider so many variables. We have y1, y2, we have 2yk. If you do the integral, okay, because all of these y's have a range of the taking values, okay, from the minimum value to the maximum. If you consider the integral, you integral all of these, then the rest part, for example, you try to get the marginal distribution of y1, but all of this part will be integrated out. The left part is the marginal distribution. That one is, in this case, it's univariate because we only have one left. But you can also keep these two and integral the remaining part. Then in that case, these marginal distributions is bivariate normal because you only have two left. And you can just do the integral of any subset of that. So the final distribution are also multivariate normal. And for conditional distribution are also multivariate normal. What does that mean? Conditional. Okay. If I fix the value of y3, for example, I only consider the students who have dry writing score as of some specific scores. Conditional on that score, that group, that particular group students also have the distribution multivariate. If we condition on this value, the remaining variables are still multivariate normally distributed. And also you can condition on SAT. Okay, you fix SAT score at some value, and for example, the verbal score at some value, and the remaining conditional distributions are still multivariate. So it is still very strong. The next property, linear combinations of y are multivariate normal. How are we going to understand that? If you know all of these variables, I can do a lot of linear combinations. For example, 2y1 plus y2. Or you can think about a very simple case. I'm going to consider the average of 3 GRE scores. That is a linear combination of y1, y2, y3. So that average follows a normal. Okay, any linear combination follow normal. And if you have more than one variable, then it's multivariate normal. If it's one variable, then it's univariate. So we have y1 plus y2 plus y3. Average. Suppose this is a z-score. GRE quant, GRE verbal, GRE writing score, that is the average score. This value still normal because of these three is normal, okay? And then you can do another kind of like any kind of linear combination. For example, the average here times 2 plus SAT score. Okay, SAT suppose it's YK or any kind of y. The combined score is still normal. Okay, linear combination are all normal. And we have another good property, zero correlation among variables implies that they are independent. But how to understand that part? Okay. If you calculate the correlation of two variables, if that correlation is 0, definitely those two variables are independent when these two are normally disputed. Only when these two are normally disputed, the 0 correlation means they are independent. But in general case, if you don't know the distribution of these two variables, if you calculate the correlation of these two variables, which is 0, then it does not necessarily mean that these two are independent. Sometimes they are dependent, but still have the correlation 0. But if it's normal, definitely it's independent. That's good property for multivariate normal. So based on all of these good properties, multivariate normal, or just normal distribution, becomes the most popular distribution, most popular assumption for our model, okay, including SEM or other popular models. Oh yeah, this is the bivariate normal. Okay, so if we focus on two variables, X and Y, then you can have that district. Okay, again, two variables, then it's not a curve anymore, it's a surface, it's curved surface. Okay, this is example. And what's the math definition? Again, we have a definition. We have a density function here. The function, the probability function of Y. This Y is again the vector. Vector. Okay, each variable can take a very special value. What is the probability of that set of vectors? We have this formula. Okay, 2 pi times k divided by 2. K is the dimension of this normal. And here, sigma, determinant. Sigma is a matrix. We have a lot of numbers, but if you calculate the determinant, it becomes one number, it's a scalar. And then take a square root of that determinant. And then another exponential part here. Okay, exponential, look at this. Okay, this is a vector, y, I, here, this is a vector. Mu is a vector. We have k dimensions. That is a difference. And here it's transpose. The column vector become a row vector. This is a row. And then this is an inverse. Inverse, remember we have inverse definition of the matrix. Inverse of the sigma covariance matrix. And then times column vector. This is column vector, the difference between y and the mu. So a row vector times a matrix times a column vector. Finally, we have one scalar. Okay, so finally here, this is one scalar. And times negative 1/2. That's the power of the exponential, and you do the calculation. Finally, you have density part, the probability. Again, the probability is between 0 and 1. Between 0 and 1. Yeah. So here we have a note here. So the bold for vectors and the matrix. So mu here is a vector. So I use bold mu. The sigma, capital sigma is a matrix. So I use bold capital sigma. And also y. Y is bold. Y is a vector. So this is the multivariate version of normal. Previously, we showed univariate normal. This is just a very special case of the following format. Okay, this is a very general expression of multivariate normal. This is a special case of the general expression. So if case 1, let's look at that. Okay, if case 1 here, k becomes 1. So it becomes 1 square root. Okay, 2 pi square root. It's the same thing. And when k is 1, the sigma becomes sigma squared. It's just one scalar. So this sigma becomes sigma squared. And the square root is the same. And the exponential here part is the same. And all of these are the same. And here, if we only have one vector, k equals 1. So y just one scalar, one number. Y minus mu. Mu again is just a number. So this is a scalar. Scalar transpose itself is the same, just like this one, okay? And sigma inverse. Sigma, if case 1, becomes sigma, sigma inverse, just reciprocal of sigma square, I'm sorry, and the y minus mu. So this is the special case of the multivariate normal. Okay, any questions about normal? Okay, any question about the normal, univariate normal, multivariate normal? Yeah.
When you look at normal distributions, you're mainly looking at your y, right? One, you're not looking at your x. You're looking at every single variable to see if you have it all.
It depends. in our SEM, you're gonna include independent variable and dependent variable. And also independent variable include a lot of variables, so it's a vector. So that's why in SEM, we will see a lot of matrix because we are talking about a bunch of variables together. We have a lot of, okay, theta matrix, psi matrix, sigma matrix. We will introduce all of these matrix, and you can also calculate the sum, very simple version of this matrix, okay? Yeah, so that's why the matrix algebra is very important for this class. Any question? Okay, next, let's look at a new concept. Not new, all of these are review. Okay, you have already known this concept in the previous class. So let's look at function called the likelihood function. Likelihood, it's kind of like a probability. It's likelihood. What is the definition of likelihood? This is a density function. Density function of y, of one variable. So if you have a lot of sample size, suppose the sample size is here is n. If you have n observations, each observation have their own density function. You're gonna times all of them together. Okay, the product of all density function is our likelihood. Likelihood, it's kind of like the probability to getting all these n observed values. So it's a product of each probability function. It's called a likelihood. But the likelihood is tiny. Think about that. Okay, so here, I don't know how many students, suppose we have 15 students. Each student, suppose we have 0.5 probability. So it's quite fair. Okay, so each student have 0.5. Then the product of 15.5 becomes tiny. 1/2 times 1/2 times 1/2 times 1/2 times 1. So the final likelihood becomes really small. So it's not easy for us to do a lot of calculation because that number is 0.000, maybe a lot of zeros. It's tiny. Then we take a log function to make it relatively larger. Just for calculation convenience, we can have a transformation of the likelihood. So think about the likelihood. Okay, the likelihood, of course, the likelihood is between 0 and 1. It's again, it's a probability. It's a product of a lot of probability values. So this one is between 0 and 1. And it could be very, very small. Suppose, okay, I gave an example. So each student 0.25, 50% is not low. But if we have the product of so many 0.5, so that number is very small. So it could be very close to 0. And then we take a log function. It's log of the likelihood. What is a log function? Log function like this, okay? Okay, so here's 0, here's 1, okay? The probability, likelihood, this is a likelihood. Log likelihood. Likelihood function is performed like this one, okay? I'm sorry, so just the color just disappeared. I'm sorry, so let me check that table. Maybe there's some markers on that.
You have the
It's a paint. The board being wet doesn't help either.
yeah.
Okay, so let me try this one. Good. Okay.
That's
So
good.
this is 1, this is 0. Log function is just like this shape. So if you have likelihood value between 0 and 1, which is tiny around maybe around here. If you take a log function, log like it becomes really large. It becomes, if you have like this value here, becomes this value. Okay. So it increases the magnitude of the likelihood function. It's easier for us to do a lot of calculation. And also, log is not our final. Sometimes we need to times -2 log. So this value is called a chi-square value of a model. So later on, we will see a lot of chi-square values. For model evaluation, we mainly focus on these chi-square values. Chi-square value is kind of like this, okay, likelihood value of a model and the log and times -2. So log value is here. All of these are negative value. But if you times -2, it becomes positive. It just becomes larger. Okay, it's positive and also times 2. So the number becomes very large. For a larger number, it's convenient for us to do a lot of calculation. So that's a log, okay? That's a likelihood. So we call this one log likely. We use a lowercase of L, log likely. And the capital L, we call it likelihood function. So what is logarithm? I just show you the function. Okay, perform like this. But what is the mathematical version of the logarithm? Log actually is an inverse function of an exponential function. Okay, so suppose this is a exponential function. We have a base and y is a power, and a to the power of y, we have x value. Now we want to get the power. So the logarithm is a function to get the power of x with the same base a. So it is the inverse function of the exponential function, okay? And this is actually very, very common, okay? So logarithm is another way to write exponential function as exponent is a power, okay? And instead, in engineering, in science areas, we use log a lot. And here we have a base, a here. We have different value of base, okay? So for example, if base a is 10, that family, okay, that family is called a common logarithm. Okay? And in science and engineering, they use a lot of the common logarithm. You can also change the a base to another constant, for example, a Euro constant, which is 2.718. Okay, it's roughly that number. If we take that e as our base, then it's called a natural logarithm function. And again, it's used in math or in calculus, okay, or in science, a lot of areas use a natural logarithm calculation. So log is powerful, it's useful. Let's look at the rules of this function. Okay, first, let's look at this rule. So we have log function here, a base, and here we have x to the p's power, okay? So we can take this p outside this log, okay? The p, the power here, take it outside of the log, becomes a p times the log function here with the same a base. And if we have this version, okay, a to the x power, but here the log with a base. So these two are the same base, log base a. Here we have a base. We can cancel it out because these are two reverse. It's canceled. It can be canceled. It just becomes its original x. Okay. And the same thing here. If we have a to the power of this log, and the log has the same base here, we can cancel these two a's. So finally, this is just x. Okay. We cancel it out. Exponential function of logarithm is canceled. We have the original x here. And these rules, these two formulas are really, really important because we're going to use it a lot later on. Okay. Log of a product of two variables is the sum of two logarithms. The product becomes a sum. We just decompose the product into a lot of components, and we can just get the sum. That's the final result. Log of a ratio, okay, x divided by y is the difference between two logarithms. Okay, so we just change the division to subtraction. That's really important because actually, you know what? Because we usually use log likelihood. The likelihood, think about likelihood, is a product of a lot of density functions. So we can transform the product into addition. So we can have a lot of addition. Okay, we will have a lot of components of logarithm log for each density function and then get the sum. Okay. And we also have another rule called the change of base. Originally, we have base A. Log with base A, x. I want to change it to another base, for example, B. I want to use B as our new base. Then how to do the transformation? You can just use a new base here, log, but you have to decide, you have to divide it by log with a new base with A value here. A is an old base. So by using this way, you change the base A to B, okay? And you have this constant. Actually, these are all constant because A and B are constant, okay? However, these two are not correct. These two are wrong formulas. These two are very close to these two formulas, but it's different. Look at it here. Okay, look at this, the correct version. Log of product is sum of two logarithms. Here, log of sum of two variables is not the sum of two logarithms. This one is wrong. This one is wrong. You cannot just divide the sum into these two logarithms. Same thing. Log of these two differences, okay, is not the differences between these two logarithms. But for ratio, it's correct. Okay, division becomes subtraction. So production becomes summation, but not these two. This is a sum. This is the difference. No, you cannot use a log to do the decomposition. Okay, so please take care of these two wrong formulas. Okay. Cannot apply into logarithm. Okay, any question about likelihood, the log likelihood, and the logarithm? Any question? And why do we want to use this function likelihood? Because there's one famous estimation method called the maximum likelihood estimation method. We're trying to maximize this log likelihood. And in practice, actually, we maximize the log likelihood function, trying to get the parameter estimate of our model. That estimation method is very, very powerful. So we have to mention these concepts. What is likelihood? What is a log likelihood? Okay. What is the rules of logarithm? Because we're gonna use these rules when you do the MLE, okay, maximum likelihood estimation method. Any question? And again, if you are not familiar with those formulas or the concepts or the rules, you can just, keep this available as a quick reference. Okay, so when you use them, you can just go back to check those rules. Okay, now let's look at another topic, regression. Regression, again, it involves two variables, at least, okay, at least two variables. Of course, you can have three or four. One independent variable x here, one dependent variable here. So we're gonna use linear association. We're gonna look at the change of these two variables to predict. Okay, we can predict the y value based on the x value. Okay, so linear regression, of course, including ANOVA. ANOVA is a very special case of linear regression. Okay. Okay, let's start with a very simple case. Simple linear regression. Simple linear, simple. Why it's simple? Because we only have one independent variable. Suppose it's x. So x is our only independent variable in this formula. And then we have another variable, which is dependent variable y. So y is predicted by x. Of course, we have some coefficients. We have A coefficient, we have B coefficient, and also we have some residual part, the random residual part. So what is A? A is an intercept of the regression line. What is B? B is the slope of the regression line. Okay, and the E part is the random error or the residual. So how to understand the meaning of A, meaning of B? What is the meaning of intercept? Intercept. This is the regression. Okay, regression. Everybody should be familiar with those concepts. Okay, intercept. Let me explain these terms in our verbal language, just common language. Okay, so we have x, we have y here. Okay, intercept is the expected value of y when x is 0. X can take a value, okay, a lot of values, 1, 2, or 3, or even -1. Okay, okay. But when x is 0, the expected value of y is 8. So this is our original formula. If you take the expected value, okay, expected value of y, A is a constant that follows the rules of expectation. Constant becomes itself expectation. When y is, when x is 0, this becomes 0. Also, you need to know the expectation of random error or the residual. But in many cases, in most cases, we assume the residual, the expectation value or the average or the mean or the residual is 0. So this part goes to 0. So the expected value of y when x is 0 is our A. A is the intercept, which is expected y when x is 0. So it's really important to understand the meaning of A. And how about B? Slope. How to understand the meaning of slope? Okay, this is expected change for slope. It's change. Okay, we're gonna look at the change. What is the change? When x increases by 1 unit, what is the change in expected value of y? That change is our slope B. So originally we have x here. If I increase the x by 1 unit, we have a new y. Okay, after the change, after we increase the x value, we will have a new y. What's the difference between the old y and the new y? It's just B. Okay, let's just follow. Yeah, let's just follow this question through calculation. So A keeps the same, A here. B keeps the same, okay, plus B here. This is a new x residual. What's the difference between these two y? Just first, you're gonna extend it. Okay, let me open this. Expand this part. Okay, A plus B times xi plus b, because here that's 1 here. And then we have the ei here. Get the distance between the new y and the old y. We cancel a here. We cancel bx here. We have e cancel. The remaining part is b. Okay. The difference between these two parts. Expect 1 because we have the residual here. We have a new residual, but the mean for these two residuals are all 0. So the expectation value are all 0. So 0 minus 0 is 0. So the expected change, y change, is our b. B is left over by comparing these two y's. So the meaning of the slope is expected change when x increases by 1 unit. Okay, and A is expected outcome y when x takes a value of 0. Okay, that's the definition of A and B, which are really important. Okay, and then how to get the A and B? We just explained the A and B, but how to get this value of A, value of B? And then we have a lot of estimation methods. The most popular one is called OLS, ordinary least square estimation method. Least square, okay, minimum square. Actually, I think I have some, yeah, I have the explanation of this method. What is least square? Minimum squared. So we try to minimize this term. What is this term? It's a sum of squared residual. E is our residual. Least minimize. Okay, minimize this term. This, although it's short as a square, but actually the sum of squared residual. So how to minimize this term? If you took calculus, you know how to maximize a term, you know how to minimize a term, right? You need to get the first derivative with respect all the parameters inside this form. Actually here, the residual is observed y minus the expected y. So we have two parameters included actually in this form. We have A and B. So with respect to these two parameters, A or B, we got the first derivative, make it 0. Okay, with got the first derivative with respect to A, make it 0, one equation. Calculate the first derivative with respect to B, make it 0, second equation. Solve these two equations together. You have the solution of A and B. You also need to make sure the second derivative is positive so that you can have a minimum, okay? And then after you do that calculation, that is the final solution, okay? B is estimated like this ratio. What is this ratio? The top part is a covariance between X and Y, covariance between X and Y. What is the bottom part? It's the variance of X. This is the variance of X. The ratio of the covariance between X and Y divided by the variance of X is the estimate of the coefficient of slope, B. After you obtain this B, you can also estimate A. So it's a mean of Y, mean of dependent variable, minus the B here times the mean of X. So you have A. You have the A parameter. So these two estimates are obtained by using the ordinary least square estimation method. Okay. So this method was invented by Gauss, okay, when he was 18 years old. Yeah, he's totally genius. Okay, so this is another version of least square. So we have the regression line here. These are observed dots here. And for each dot, because we have the regression line, we have the residual. So residual, how to define residual? It's actually the observed y minus the expected y. Expected y is located on the regression line, decided by A and B parameters. Okay. The expected y here, the distance, the vertical distance between these two dots is the residual. Okay, observed y here, expected y here, the distance, vertical distance, residual, the residual, and we make it positive because sometimes the residual is negative when the dot is below the regression line, then the residual is negative. When the dots are above the regression line, the residual is positive. So in order to make it a sum, because if it's sometimes it's positive, sometimes negative, sometimes we can cancel with each other. But we don't want to do that. We make it positive to get the sum, so that we can minimize this term. And this is another version. So for each dot here, we have vertical residual here, and if you square it, become this square. Okay, for this dot, we have the yellow square. For this dot here, we have the white square here. For this dot here, we have blue dot here. Get all the sum of all these squares, we have the total square here. We're trying to minimize this total sum of squares by changing the value A and B. So at some point, we will make this sum of squares minimum, and we stop there. That A and B is our final solution of the ordinary least square estimate. Okay. Of course, this is just one version of least square. We have a lot of versions of least square. We can put a weight, which is called a weighted least square. This is the ordinary least square. We don't have any weight here. We can also use the iterative procedures, which is called iterative least square. We have many versions. Okay, here we just give a really simple example by looking at the simple linear regression. We only have one independent variable. But suppose we have many independent variables. We have x1, x2, x3. Okay. Then, of course, the A and B are not so simple. We have a matrix form. We have matrix form for the regression formula. Okay? So here we have dependent variable y. Y again, it is a vector. It's just not one variable. It's just a combination of several dependent variables together. We have x. X here is a huge matrix. It's a matrix combination of all independent variables. And then we have beta. What is beta? Beta is our parameters. It's a vector including all the parameters in our model. And then we have residual. Okay, so that's very abstract. That's very let me just show you the detailed form of all of these matrix. Okay. Okay, so now consider a lot of dependent variable y. Okay, y is a vector. Y is a combination of y1, y2. We have y and y. Suppose we have n individuals. Outcome. Okay, those are outcomes. And then we have x. Look at the dimension of the x. What is the dimension of x? N by 1 plus k. Why it's so weird? Why it's so? Let's look at. Let me just space here. Okay, x matrix x. The dimension is n by 1 plus k. Remember what's the meaning of dimension? The first component means how many rows, the number of rows. The second component is the number of columns. So that means in this matrix A, I'm sorry, X, we have n rows. 1, 2, 3, 4, 2, n rows. And we have 1 plus k columns. 1 plus k columns. The first column is just 1, 1, 1, 1. Okay, 1, 1, 1. All of these elements are 1. That's the first column. That's the first column. First column here, 1. And then we have different independent variables. x1, x2 to xk. Suppose we have k independent variables. Those are predictors. Those could be high school, a lot of scores. We can predict the Y score here. For each independent variable here, we have the observed value for each. Suppose these are participants, individual. Okay, x1 for the first individual. Okay, x2 for the first individual. I'm sorry. So these are all x1. Okay, x1, but for first individual, second individual, third, but all variable x1, independent variable x1. And then for x2, we have all the individual scores. For xk, we have all the individual scores. So combine them together, all of these combined together, we have X matrix. So that's why the number of columns is 1 plus k. The k is the number of independent variables plus 1. Then you on total have 1 plus k columns. That's X. And beta. What is beta? It's a vector, including all the parameters available in this model. Specifically, including A, B1, B2 to Bk. So the number of parameters is 1 plus k. The 1 is the intercept. This is the intercept. These are all slopes. These are coefficients. Because here we have k independent variables. For each independent variable, we have their coefficient or slope, corresponding slope, b. So here we have k independent variables. We have k, b for coefficients or slopes. So together we have 1 plus k. We have 1 plus k parameters in this model. Okay. And we have the residual. Okay, finally we have the residual. Residual is kind of like a B1, epsilon1, epsilon2, or E1, E2. Okay. And population version we use epsilon, but if it's a sample version, we can use E. E1, E2 to En, same dimension. So that's the residual part. After we have this form, the estimate of the parameter here becomes really easy. This is the estimate of B. Again, it's based on ordinary least square estimation method. Transpose of the huge matrix here, matrix the transpose times the original matrix X. After you got the product, that is inverse of the product of these two matrices. And then times the transpose of the X, and then times the vector Y. So all of these are observed. We know the independent variables for each individual. We know the dependent variable for each individual. So all of these are known values. And then we have estimate of beta or estimate of B. That's a solution for the ordinary least square estimation method. As I mentioned, there are a lot of estimation methods. Ordinary least square estimation method is just one of them. We have another one called the maximum likelihood estimation method. If we use maximum likelihood measurement method, you can have another set of estimates. With the same goal, the parameter estimate, we can have different approach, different roads to reach that final goal. If we use maximum likelihood estimate, you will have another set of estimates. But when you have multivariate normal distribution assumed, the results are exactly the same. Only when you have multivariate normal distribution assumption, the maximum likelihood estimate is this version. It's exactly the same as the ordinary least estimation method. But for OLS, no assumption, no normal distribution assumption required, needed, no assumption needed. But for maximum likelihood estimation, you have to assume some distributions. But if you have normal, then you have this result. Okay. So both are very elegant results. But of course, if you assume chi-square distributed, the estimate of beta will be totally different because you change the assumption. So the derivation will be different. But if it's normal, then these two are the same. Any question for the review of regression? Yeah, we start from the simple linear regression. We talk about the ultimate least estimation method. And we look at the matrix form of linear regression model. And we talk about the estimates, okay, OLS estimate and MLE estimate. Okay, so any question? Okay, then let's look at assumptions. Okay, linear regression is powerful. It's also quite easy to obtain those estimates. It's very powerful, but you cannot use it for each scenario. You cannot just apply this model in all cases. There are a lot of assumptions for that model. If those assumptions are not satisfied, you may not use a regular linear regression model. You're gonna change your model a little bit, okay? So what are those assumptions? Suppose X is independent variable, Y is a dependent variable. In linear regression case, X is a fixed variable. This is very important. Y is a random variable. That's why we have Y equals A plus BX plus some random error. Random error is on Y, not on X. X is fixed. Although X has some different value, it has the X1 value for individual, one for individual. But these values are predetermined. X is not a random variable. But in SEM, this assumption can be relaxed. We can also assume X is a random variable. This is more general, okay? And also we assume X and Y have linear association. If there's a nonlinear association, we're gonna do the transformation first to transform the outcome Y or transform the Y into some function. And then we do another analysis. For example, IRT, so it's not linear association, okay? So we also have a lot of assumptions for measurement errors. E part or the epsilon part. In the population version, we use Greek letters, epsilon. In the sample version, we use Latin letters, E, okay? But all of these means the residual part, okay? For the measurement error part. If we just want to get the point estimate A and B, those assumptions are required. What are these? Okay, let's look at this. Let's look at this one. Mean zero. What does that mean? As I mentioned before, the exact value of E is assumed zero. The exact second residual or the measurement error is zero. Okay, so the mean was average. The expected value of all of these errors zero. So this is our first assumption. We assume that this is zero. Okay. Second assumption, independent. Okay, E1, E2, E3. Okay, all of these independent errors associated with one observation are not correlated with another, or errors associated with another observation. All of these E residuals are independent. So that means this E, the measurement error, does not depend on the previous residuals. In time series, dependent. sometimes time series. Okay, so the observations depends on the previous one, but we assume here these are independent. Also, homoscedasticity. Okay, it's very hard to pronounce. Homoscedasticity. Okay. So what does that mean? The variance of errors are the same. Here, this is the citation. How about the variance? The variance. If we change the variance part, it's not 0 anymore. It's a constant for all of these observations. Okay, variance. For E1, sigma squared, suppose. Variance for E2, suppose it's sigma squared. All of this variance. It's constant. It's the same. It's a homo, okay? Scedacities, okay? So, variance of errors at all variables is constant. Also, the errors and independent variable x are uncorrelated, independent. So, the error part, where's the equation? Okay. We have the equation. Okay, suppose we have like this. The predictors x here and the errors e here are uncorrelated. We decompose this into two parts. That's our assumption. Uncorrelated with x. So this is the unexplained part. Okay, this is the predictors. So we have predictors x, we have residuals. Those are not predictors. We assume these are independent. We assume these are uncorrelated. That's our assumption. That means there's no correlation or covariance between x and e. This is also important for our SEM assumption. Okay. If you just want to obtain the point estimate A and B, or of course B1, B2, B3, all of these, those assumptions are enough. You don't need to put any other assumption. But when you want to do more, when you want to do a test, get a p-value, if it's significant or not, if you want to get the variance or the standard deviation part, you need to add one more assumption, which is a distribution assumption. We should put normal or other distribution. Okay, normal is the most popular one, but you can also put another distribution. You can assume it's normally distributed or other type of distributed. So those are assumptions. Great, that's for linear model. Okay, how to do a diagnostics? Okay, this is a very simple way. You can just put the residual. Look at the plot of the residual. If you have residual like this, that's good. It's good for linear. If you have residual like this, no. Okay, because actually that is not linear associated between x and y. We should use a curve to do this. If you have residual like this, no. Because the variance for the smaller x is small. The variance for larger x is large. It's not constant. It does not satisfy the previous assumption. So let's move forward to SEM. We talk about regression. In regression, all the variables involved here are observed variables. We have x, maybe we have x1, x2, x3, and we have dependent variable y. All of these variables are observed variables, no latent variable involved. What does that mean? We assume that observed variables is just perfect measured. There's no random error. We got the observed variable just like the true value. But in reality, we cannot measure a variable without any error. We cannot measure it perfectly. So we have to consider some errors when doing the measurement. So we have the true score, we have some measurement errors, combine them together, we have observed score. Okay. So if we treat the observed value as our true score, then maybe the bias we will have some bias. Okay, the coefficient, the standard errors, the effect size obtained from the observed variables may be biased. So in these cases, we have observed variables and also we have latent variables, which is a true score, which is a variable we truly want to measure. Okay. So structural equation modeling can handle these cases. Okay. It's a generalized linear model. SEM is big family. It's regression included in SEM. Regression is sub-model of SEM. SEM is more general, using observed variable and the latent variable together to determine the complex relationship between all of these variables. Between latent constructs, sometimes we call it factors. Yeah, we use construct or factors as our latent variables. Yeah, factors, latent factor, and observed variables. We just draw different lines to connect these variables. Sometimes it's observed variable, sometimes latent variable. We just look at the association or the relationship among them, but more complex than linear regression. For linear regression, it's quite simple. We have independent variables, we have dependent variables. The flow is from independent variables to dependent variables. That's it. But for SEM, you can go further. Okay, the dependent variable can cause another dependent variable, can cause another dependent variable. Okay, so we can have a lot of trains. And the focus is a relationship. We're gonna look at the variance matrix, variance and the covariance matrix a lot. The focus is variance, means the components of all elements. Okay, means the association, the variation of all of these variables. So let's look at some examples of SEM. Okay, all of these are SEM. We have some circles. Circles means factors or latent construct or latent variables. Okay. And we also have observed variables. We use squares or rectangles to show observed variables. And we have a lot of lines. Okay, we have straight arrow. Okay, we have also the curved lines, double-headed, single-headed. We also have the residual part here, latent factors here. We have a lot of indicators. Those are examples of our SEM. And then we can also report the model fit. Okay, is the model fit the data well or not? Okay, is that good model or not? We're gonna report the all of these indexes. Okay, so that's for the review and the very brief introduction, or very brief review of the prior knowledge. We don't have any assignment for the first session. Any question? Yeah.
If we wanted to do the exercise, is there a key available that we can check our work?
For the review part?
Yeah.
Yeah,
Just
you
to
have
refresh on
document,
stuff.
just check the document. Yeah.
Yes, ma'am.
Yeah.
Okay.
And for this part, there's no exercise. I just give you a review, no
Yes,
exercise. Yeah. So actually, for regression, you can just read the previous regression slides. Yeah. Okay. So any question for the first session for the review part? Okay. So next, after the break, we can have a break, and after break, we can formally look at the introduction to SEM. So how about have a 15 minutes break? Yeah, after 15 minutes, we're gonna come back and then look at the, yeah, okay. Thank you. Let's continue the second session.
Yay.
Oh, yeah. During the break, okay. Any question?
No, I don't, sorry.
During the break, some students can ask why we have 1. Okay, the column 1 here. Let me explain it first. Uh, Okay, so this is our X. And this is our beta. So we have the X here. We have beta here. This is our beta vector, and we also have the epsilon. Epsilon is for E. It's also vector. Okay, so vector E1, E2 to ES. It's a vector here. So we have Y. Of course, Y is also a vector. Y1, Y2, Yn. So why do we have this column? Why do we need to add a column 1 in X? Because when you do the matrix algebra, okay, so this is X times beta, matrix times the column. How do you want to do the matrix algebra? Okay, the row here times the column here. So if you do the calculation, 1 here, it's a row. It's inside of the row, the first row. Okay, 1 times A plus X1 times B1, okay, plus X2 times B2, okay, and we continue. We have XK times BK, and of course we have the residual. Okay, we have the E1. This is our X. This is our Y1. So Y1 is linear combination of the intercept B1 times X1, B2 times X2 to BK times BK, BK times XK, and the E1. This is the first observation of Y1 here. Same thing, Y2. For Y2, we have second row times the same column. So we have Y2, again, 1, the 1 here, times A, plus for the second individual, okay, this is for the first individual we have. We also have the second individual, okay, B1 times X1, B2 times X2, BK times XK, 2, okay. And for the second individual, the X value for the second individual. So we have all of these combined, we have Y2. So this is a linear combination. This is a linear regression, multiple linear regression, the individual version. This is the matrix version. So the 1, 1, 1, 1 here actually is prepared for the A, because the coefficient for A, another component for A is 1. So you need to make sure that we have 1, 1, 1, yeah, so that we can include the A in our equation. And here, those are independent variables X, okay? And we have the coefficient for X. So combine X and the B together, we have the expected part of Y. So that's why we have to include the column 1 in X, just for the intercept, okay? Just for the calculation of the intercept. Okay. Session 2, we are going to do a brief introduction, and then we look at the path diagram, we look at the detailed models of SEM. So why? Yeah, introduction to SEM. Why do we want to use SEM? Or why do we want to study SEM? And what's the history of SEM? And the path diagram and these models. So actually in the previous review, when we talk about assumptions, we mentioned these slides, okay. We use linear regression in a lot of cases, in many cases. But there are a lot of assumptions. First, about the measurement. All the variables in linear regression are observed variables. we assume that the observed variables is kind of like a true variable. It's a variable we want to measure. So there's no measurement error, okay? So no latent variable is involved in linear regression. But in reality, variables are not measured perfectly. Okay, so we have observed variable, we have true variable, we have some measurement errors or some noise. It's due to some questionnaire or due to the understanding of this question, due to some other reason, we have some measurement errors. So if you still use a regression to do the data analysis, the coefficients or standard errors or effect size might be biased because actually those variables are not. Those are observed variables, including some measurement errors, or those are not true variables. So we have different types of variables. Observed variables and the latent variables or latent constructs. So that's one reason we're gonna study the SEM. Also, look at the relationship. As I mentioned in the linear regression, the relationship between variables are quite simple. So we have independent variables, which is also called the predictors or causal variables, and we have dependent variables. Okay, so the independent variable is going to cause the dependent variable. But in many cases, the dependent variable could be independent variable or could be causes of another variable. And the relationship is more complicated than the linear regression. So we have larger group of variables, so the relationship will be complicated than just the simple case. So in these cases, we have different names. We have exogenous variables, we also have endogenous variables. It's quite like independent variables and dependent variables, but we can extend the definition a little bit, okay? Sometimes we have latent, sometimes we have observed. So we will do the explanation of these variables later on, okay? After several slides, we have the definition for exogenous variables, definition for endogenous variables. So in this case, it's how I'm going to analyze data. So we are going to use SEM. It's very general, it's a very big family, SEM, okay? So it's a generalization of a linear model by including observed and latent variables together to determine the complex relationship among them, among all of these variables. And SEM now becomes really, really popular. Okay. In stats, in educational area, in psychology area, in econometrics. Okay, so they all gonna use in business school. We're gonna use SEM. And also the previous models, for example, ANOVA, regression, test analysis, and also later on we're gonna cover the effect analysis. All of these are sub-models of SEM. Okay, SEM including all of these. Okay. We will see those simple cases, for example, ANOVA and regression. We will have examples. And we can also use SEM to do a lot of tests, or a lot of like hypothesis testing, or you have some ideas. You can use SEM to do the test if your idea or if your hypothesis is correct or not. Okay, it's good for your data set or not. Okay, and also we can do the factor regression, evaluation of latent constructs, and the incomplete data bias. Okay, for missing data, we can also incorporate that into the SEM. So we use causal model to provide us a causal analysis. Okay, a lot of like reasons. So let's look at the very brief history of SEM. I think this paper might be the first paper to introduce the SEM into this world. It's a biology science. Okay, so Dr. Wright trying to look at the piebald pattern of guinea pigs. So he trying to divided the resources of the variation resources into different parts. For example, 3 parts, okay, 3 factors. Heredity is coming from their parents, and the E, environment, common to later matters before birth, or environment, heredity, and also have the residual. Okay. Okay, so 3 parts. For example, these 2 are child of these parents. Okay, so we have the heredity from their parents, and also we have the environment, B, environment. We also have the residual part, the D part, which are different, unique for this different guinea pigs. And that is the parents. We have Saya, we have Dan. They also have their environment. They also have the B factor, the heredity. So maybe that is the first SEM paper. Okay. But that's just a paper. So we have some ideas of very simple calculations. That paper was published in 1920. So almost 100, yeah, more than 100 years ago, okay? But SEM didn't get a full developed until 1970 because we have a lot of computer programs available. With the help of the computer program, people can do a lot of like estimation, can apply that model to a lot of areas. So SEM just get boom, okay? So we have a lot of practice research in many areas. So SEM can be applied in many disciplines, including biostatistics, yeah, and econometrics, and the psychometrics, and the social statistics. Yeah, it's very general latent variable analysis. Okay. It's very broad. Yeah.
I'm trying to think of can you give examples of a latent variable versus an observed variable?
Yeah. So latent means it's underlying variable. It's not directly observed. Observed variable is just, for example, if we're trying to look at people's math ability, we cannot get the score directly. So we're trying to use different math tests to trying to kind of like estimate the people's mathematical ability. Yeah, so latent means not directly observed. It's kind of like underlying. It's latent. Yeah. Thank you. That good question. So basically, for SEM, we have different steps. Okay, so first step, you can have your own. Okay, this is actually for one part of SEM. For another branch, you can also do the exploratory data analysis. But assume that you have your own hypothesis ready, then you can do the specification, the first step. That means you have some ideas before you do the data analysis. So you have some hypothesis. Then you're gonna first step, you're gonna specify your model. What is your model specification? Put some special structure on your data. Okay, that's the first step. And then second step, you do a lot of estimation, trying to get the parameter estimate. Okay. In simple linear regression, you trying to estimate A and B, but for SEM, of course, you have a lot of coefficients or factor loadings. And then you're gonna also evaluate your model. So if suppose you have different models or alternative models, then you're gonna do some comparison. If this model better or that model better, okay, how to do the comparison, how to evaluate your model, is the model good or not? And if it's not good, then you can maybe modify your model a little bit and re-evaluate your model. Okay. And then finally, after you get the final result, you're gonna do the interpretation. So how to explain those parameters and what's your conclusion? What's your final findings? Okay, you have different steps. Let's look at a very simple example of SEM. Okay, as I mentioned, the path diagram is a very simple way to show an SEM, structural equation model. So here we have path diagram including a lot of circles, okay, circles, squares, and straight line, single-headed straight line, double-headed curves. Actually, you know what? I admit, actually, it's larger than this one. Let me. I just removed the residual part. Actually, we also have the residual part. If it's a full SEM model, we're gonna including errors. So actually, we also have the errors. Okay, we can say that it's E3, E4. Okay. Okay. Same thing for each variable on top. Yeah, I cannot reach that end, but you can just make it complete. You have E1 and E2 or Y. You can change it to Z or any other letter to show the residual. Okay. So we also have residuals for this part.
Would there also be residuals on that N1 and N2 in
Yeah.
the middle?
You're right. Here we have eta, we have C, we have C. Yeah, I will introduce those letters too.
Okay.
So anyway, this is a very simple example of SEM. We use a path diagram. So here you can see that there are different types of forms. We have some different shapes of variables. So let me explain those components. We have circles. In SEM, if it's latent, that means if it's not directly observed, we use a circle. We call it a construct or factor. Okay, construct, latent construct or latent factor. Those are latent. Residuals are also, okay, residuals, I put some residuals here. Residuals are also showed as a circle, circles, okay? That's for circles. But we also have some rectangles or squares. What are those variables? Those are observed variables. Okay, directly measured variable from our test or questionnaire or other way to collect data. Yeah, question?
So the observed variables are basically the items that were used. to make-
Exactly. So for the questionnaire, we have a bunch of items. We have a bunch of questions. The value of those items or you can say the variable indicators. Yeah, so we're gonna use the rectangles or squares. But based on these group of items, we can extract some latent variables. That one can be shown as a circle. Great idea, yeah. So these are also called indicators of a factor, indicators. Those are observed variables. So it's very important because when you see a path diagram just like this, clearly you directly know this one is not directly observed. I don't have actual value for this one. Instead, I observed X1 and X2. Those are items or those are indicators of this variable. And same thing, these are indicators of this latent variable, either one. Yeah, so those are latent part or hidden part. It's hidden. And we have some arrows. We may have single-headed arrow, we may have double-headed arrow. So let's look at these. We have, for example, single-headed arrow, double-headed arrow. Yeah. Okay, that's a very simple introduction of these forms, different components of the path diagram. Okay, next, let me introduce the exogenous variables and endogenous variables. These slides actually from my regression course. If you took my regression course, I have these slides. We have one chapter talk about the endogenous variables or exogenous variables, path diagram. So these are review slides. So for path diagram, we can, use it for SEM and actually make it, it shows a causality. Okay. So we have exogenous variables. What's the definition of this type of variable? Okay, it's a variable whose variability is assumed to be determined by causes outside of the causal model under construction. So we have SEM model, but some variables of variabilities come from outside, not inside. We call those variables exogenous variables. We have another type of model, endogenous variables. Okay, so what is the definition? It is a variable whose variability is to be explained by exogenous variable and other endogenous variable inside the causal model. Some variables, the causal, the variability is coming from inside the variables. So that type of variable is called endogenous variable. I will give you the detailed explanation. Okay, those are definitions. Outside, inside. And for arrows, okay, it is double-headed arrow, okay, two-sided, okay, double-headed arrows. Usually it's curved line with arrowheads at both ends. That means those two variables are correlated. There's a covariance among them. But which one causes which one, I don't know. Is A causes B or B causes A? I don't know. I just know that these two are correlated. Then I use a double-headed arrow. I also use a single-headed arrow to clearly show the flow of the cause and the effect. Okay, so causal path from the end without the arrow headed to the end with arrow head. So from A to B. So there you use a single-headed arrow from A to B. So that means A gonna causes B. There's a clear path. Okay, so for single-headed arrow, for example, in this way, I clearly know that eta 1 gonna causes eta 2, not eta 2 causes eta 1. So here, this is a single-headed arrow. But for these two, C1 and C2, I don't know why. I don't know if C1 causes C2 or C2 causes C1. So I just use double-headed arrows to connect these two. Okay. Okay, so we reviewed these slides for different types of variables. Yeah. And then let's look at relationship. As I mentioned, we have two types of arrows. Okay, double-headed or single-headed. That's gonna express the relationship among variables. Single-headed arrow means cause. Okay. So yeah, if you have some hypothesis, A gonna causes B, A gonna causes B, then you use a single-headed arrow. Okay, the directions from predictor to outcome, just like a regression, from independent variables to dependent variables. Double-headed arrows are also associated. Okay, double-headed arrow, correlated. So in the path diagram, actually, you can see this type of path diagram. It tells us two types of relationships. One is just like this. We have some circles, we have some squares, okay, or just like this, like this. Golden one, in the golden part, actually that is one type of relationship. And we have another type of relationship included inside the green circle, okay, green one. So these are two different types of relationships. The golden one, okay, the golden one, let me show you like this. It's called measurement model. We have some latent variable here, circle here. We have some indicators here, and of course, we have some errors or residuals here. Okay, those are residuals also use circles. Okay, so this type is called a measurement model. Okay? Between latent construct or latent factors and indicators, means squares or rectangles, indicators that measure them. So for that type of relationship, we have the measurement model. That's it. We have the measurement model. What's the meaning of this one? Okay, we use these two as our indicators to measure the latent variable Kc. Kc is not directly observed. We use these two. These two are observed. These two are directly measured. By looking at these two test scores or item scores or any outcomes to look at the true score of the latent variable here. And we have the error part. Okay, that's measurement model. Yeah, it's between latent constructs and the indicators that measure them. So we have circles, we have rectangles or squares. Now let's look at the arrows. It's really important. In SEM, the direction is always from the circles to rectangles. What does that mean? That means actually the latent constructs gonna cause the observed indicator values. If you change the latent variable's value, the outcome will be different. So this is the cause. This is the underlying cause. And this is outcome. This is a response. This is the observed variable. You cannot use a reverse direction. If you reverse that, what does that mean? So the observed variable gonna influence the inside the latent variable. No, that's not the logic of SEM. In SEM, we assume the underlying traits, the personal traits or other latent variables will influence the outcome. For example, personality. If the person is quite open-minded, then the outcome or the item to measure the open-minded will have a higher score because the latent cause, the traits is quite maybe it's quite large. Then the observed variable will be large. Okay? So the direction is from the construct to the indicator. That's for single-headed error. That means latent variables cause or drive their observed indicators. Again, that's very important logically in SEM in your course project or your personal homework. If you reverse the direction, I may take some points off because you don't know the underlying logic. Okay. And we also some measurement errors. Okay, again, the measurement errors are from circle to observed rectangles. So what does that mean? The direction is from the residual variable to the indicator. So the observed variable, the final observed variable include part of the residual or part of the error, measurement error, two latent traits plus some measurement error. Together, we have the observed variable. So the observed variable is not perfect measure this item, this latent trait. It also includes some measurement error. So that's why this one causes. So the measurement error will cause the outcome response. If the measurement error is large, okay, if the questionnaire is not well designed, it's not well designed, the observed variable might have a lot of fluctuation. because some part of that is due to the measurement error. But if your measurement error is quite small, it's quite close to the true value, then these two will close to each other because the measurement error is small. So this is combination of measurement error and the true score or the latent trace. By combining these two parts, we have observed a score. Okay, so that's why the single head error is from here to here, from here to here. You cannot reverse the direction. And there's another type of relationship called, okay, it's called a structural model. It's between outcomes and predictors. What does that mean? So let's look at this part. It's inside of the green circles, inside of the green, this one, okay? So it's called a structural model. Structural model. In structural model, the relationship between outcomes and the predictors. We have some predictors, we have some outcomes.
Is it missing errors at those?
You are
other-
right.
Okay.
We have some missing errors. Yeah, it's simplified version of the SEM path diagrams. Of course, we have some circles here.
Yes, ma'am. Sorry.
So it looks like in regression because we have some predictors, although those are circles, although these are not directly observed independent variables, but still these are predictors. These are kind of like independent variables. These are causes. And we have some outcome. And this outcome is a predictor of this outcome, okay? So the theory is that outcomes are consequence of predictors. These outcomes are consequence of these two predictors, and this outcome is a consequence of these predictors. Okay? So in SEM, one predictor's outcome may be another outcome's predictors. Okay. And exogenous construct is determined by force entirely outside of the hypothesis system. As we defined in the previous slides, endogenous variable and exogenous variables. Exogenous variables, the construct is determined by outside the system, outside of the model, not due to the inside variables. But endogenous variables, the variability is coming from inside of the model. So actually, let's look at the if you look at this path diagram, all of these can be treated as exogenous variables. Although those are latent, these are observed, but they can be treated as exogenous variables, okay? But these two endogenous variables, because the variability is coming from inside, these are outcome of these two variables. So we will have different versions of SEM. So we will show the details of the versions of SEM. Okay. By looking at the different types of endogenous or exogenous variables. Okay, so path diagram. Yeah, so by using the SEM, we can just analyze the relationship among parental depression, okay, one conflicts, or all of these relationship can be addressed by using SEM. Okay, so that's two types of structure, two types of models in SEM. And that's previously we just explained the path diagram. So how about the mathematical form of SEM? There's a very famous math equation called the Lizero model. Lizero model actually is short for linear structural relationship. Okay, linear structural relationship is called Lizero. There's a software, it's very old software, very traditional software. Lizero is still based on these models. So let's look at this model models, including 3 equations. 2 of them are measurement models, just like here. 2 of them are measurement models. One is structural model. This one is structural model. So why 2 measurement models? We divided it into exogenous variables and endogenous variables. If we set X measurement actually mainly for exogenous variables, or you can just treat this part as independent variables part or predictors part. You also have the Y measurement model, which is for endogenous variables, mainly for the dependent variable part. So X gonna call this Y. These are kind of like independent variables. These are dependent variables. Although some of them are observed, some of them are latent, some of them are observed, some of them latent, but I don't care. I just treat all of these as our X measure model. In other words, in endogenous variables, which describe the independent variables part or predictors part. This is called the Y measurement model, which is for the dependent variable part. Okay? Y is the dependent variable part. Okay? We also have a structural model. Structural model like this part. Okay? We have the relationship described between the outcome and predictors. And in the literal expression, we mainly focus on latent part. Latent Y, latent Y, latent X. We mainly focus on latent because in this example, we also have latent. Okay? We have latent C, we have latent eta. Latent C actually belongs to X measurement model. Latent eta belongs to the Y measurement model, endogenous model. This part is exogenous variables. So again, let me explain this part again. We have a lot of notations. All of these are mainly based on the Greek letters. In SEM, people just use Greek letters a lot. And they have their special meaning for each Greek letter. For example, here, we have tau X, tau Y, we have alpha. All of these means intercept, just like linear regression. We have intercept for X, intercept for Y, intercept for this data part. And so let's look at the notations. Tau X, tau Y, and alpha are intercepts. And then we have X and Y. Those are observed variables, observed independent variable, observed dependent variable. Okay. Y, X, Y, observed. It's indicators of C and eta. Okay. This is called C, latent X. This is eta, latent Y. Yeah, so we have this latent dependent variable. Okay, eta is latent dependent variable or endogenous variable. Okay, C is latent independent variable or exogenous variable. So if you look at this diagram, X measurement, okay, X measurement, C are latent exogenous variables. X, X1, X2, X3, X4 are observed exogenous variables or observed independent variable part. These are latent independent variables part. And all of these are Y, okay, Y measurement part, okay. We have some indicators. We also have some latent Y. We call it eta, okay, eta 1, eta 2. Eta 1 is measured by these 2 indicators. Eta 2 is measured by these three latent observed indicators. So yeah, so we have the observed part, latent part, and we have intercept, and also we have a lot of matrix. Okay, beta, gamma, all of these lambda, all of these are matrix. Okay,
And that's why they're bolded.
exactly.
Okay.
All of these are bold. This is a vector. This is vector. This is a matrix. This is a vector. This is a matrix. Vector, vector, matrix, vector, 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 vector. All of this vector. This is a matrix. This is the loading factor loading matrix. When we talk about factor models, we will go back to look at the details of lambda x and also for lambda y, and also how to estimate those parameters. Lambda, for each lambda, how are we going to estimate this lambda? Beta matrix. Beta, this one tells us the relationship between eta and eta. From eta to eta, there's a relationship. Let's look at this diagram. Yeah. If eta is the vector, eta 1, eta 2, you can use a matrix to tell the relationship between eta 1 to eta 2. Yeah, everything, we will have example to describe the data here. Everything's stored here. The direction from eta 1 to eta 2 will be described inside of this matrix. This matrix tells us the relationship inside eta, between eta. This is another matrix, gamma. Gamma tells us the relationship between C and eta. From C to eta, what is the relationship? Okay, from which one to which one? Oh. 8:20. Okay, almost. Okay, we have 5 minutes left. Let me just finish the explanation here. Then we can stop. Okay, we can pause here. So we have matrix. Gamma decides the relationship between C and eta. And we also have the residuals, zeta. Okay, residuals, zeta part. That's why here we have the zeta derivative. Yeah, so all of these are coefficient. This is the coefficient for endogenous variables from eta to eta, both eta or endogenous variables. Gamma is a coefficient matrix for exogenous variables from C to eta. Okay, what's the relationship from C to eta described in this gamma? And we have the residual, okay, eta, delta, epsilon, these are measurement areas for x and y. Vector loadings for x and y. You can see that we use a lot of like Greek letters. Actually, all of these Greek letters are used in SEM. So let's look at these numbers or these letters. Okay, we have alpha. Usually we use alpha for intercept. Okay, we introduced the alpha in the previous slides. Beta, we use beta for coefficient. For example, like the linear regression, we have x times beta. The beta for coefficient. Gamma, sometimes we have like a gamma coefficient. In the previous, we have gamma coefficient. Okay, tell us the relationship between the exogenous variable and the endogenous variables. Delta, usually it's used for residual part. It's like a structural model. We have the delta part. Delta, epsilon, again, we use it for residual part. For the x measurement or y measurement, we have epsilon. Zeta, also zeta used for residual part. Okay. Eta usually is for the latent latent dependent variable as the endogenous variable. Beta usually for the matrix for some residuals. We will see a lot of matrix. Okay, so beta usually we have the beta matrix. Iota, kappa. Okay, kappa sometimes we use the factor loadings. Lambda also some factor loadings. Mu usually for the center. Okay, for the mean part, mu. And the nu, we can use it for the residual part. C, we can use it for the latent exogenous variables. Omicron, okay, pi, we have rho for correlation, sigma, we have sigma coefficient or sigma square, variance part. Tau, we have a tau x, tau y, okay, we have a lot of tau. Epsilon, we use the residual part. We have phi, again, we use phi for the covariance matrix for the latent factors. Phi11, phi22, also those are for the covariance matrix for the latent factors. Chi, okay, chi-square value, okay, also a lot of chi value. Psi, also use it for residual matrix, psi matrix. Omega, we have omega. So all of these Greek letters are important, and we use them in our SEM math equations. Okay, so usually they have their own specific meaning, but sometimes people, use different notations, but you have to put the note. Okay, eta here means what? To make a clarification. Okay, the lambda here means what? To explain those letters. Okay, I think I need to stop here because now it's 8:25, and then we're gonna look at the detailed X measurement, Y measurement, and structural equations for the specific path diagram next time. Okay, how to decide the beta matrix, how to decide the gamma matrix, lambda, we're gonna look at that next week. Any question before you go? Okay, before you go, any question? Any question? How about the pace? Is that too fast? Or should I slow down?
Oh, it's good.
It's good? Okay, good, okay. And if you have any question, just email me, just let me know, okay. And again, if you have any symptoms of COVID-19, just let me know and I will have the Zoom meeting for you. Okay, I need to stop here.
Thank you.
Thank you, yeah, that's all. You have a great night. Yeah, bye.